Welcome to the pod Biomanufacturing and Fermentation Technology. In this episode, we translate microbial science, process engineering, and manufacturing realities into insights that scale.
Welcome to the debate. Today, we are taking a rigorous look at one of the most persistent, highly technical challenges in biomanufacturing, specifically optimizing methanol feeding in Pichia pastoris. The fundamental task at hand is really a delicate balancing act. On one side, we have to prevent the cellular toxicity that inherently comes with methanol accumulation, but on the other, we are trying to maximize the induction of the AOX1 promoter, which is, the genetic workhorse that kicks into high gear the moment Pichia metabolizes methanol to drive our target protein expression.
Right. And it's a notoriously tricky balance. I mean, if you overfeed, you poison the culture. If you underfeed, your protein expression just stalls out entirely.
Exactly. Which brings us to our focus today. Our discussion centers on a specific solution kit detailed in our source material. What makes this kit remarkable is that it's designed for a rapid 10 to 14-day implementation window, and the outcomes are massive. A 40% reduction in the induction phase duration and a 25% increase in overall titer, which the data attributes to reduce cell stress.
Yeah. It presents two distinct methodologies working in tandem here. First, a direct online methanol sensor, specifically utilizing Raven Biotech hardware, driving closed-loop PID control to hold the concentration tightly between 1.0 and 2.0 grams per liter. And second, an off-gas analysis strategy targeting a respiratory quotient, or RQ, of approximately 0.65 to 0.75.
Two very different ways of looking at the exact same bioreactor.
Completely different.
Precisely. And my position today is that the mechanical precision of that direct online methanol sensor and its closed-loop PID control is the fundamental driver of these optimizations. By maintaining that rigid 1.0 to 2.0 grams per liter concentration, we are physically preventing the toxicity that would normally derail the process. The hardware provides the stability that makes everything else possible.
And I will be taking the opposing view. While I certainly don't deny the utility of, dropping a modern sensor into a tank, my position is that the respiratory quotient-based control strategy is the truly critical framework here. The biological reality of Pichia pastoris is that it requires dynamic metabolic monitoring. A static environmental target simply isn't enough. By analyzing the off-gas to maintain an RQ between 0.65 and 0.75, we are directly measuring the actual physiological state of the cells. You cannot measure cell stress by merely looking at the methanol concentration floating in the liquid. You have to look at how the cell is breathing. That is what RQ control achieves, making it the indispensable core of this optimization.
Let's break that down because I think we need to look at the mechanics of what the hardware is actually doing. When we talk about toxicity prevention, we are fundamentally talking about environmental control. Integrating an online methanol sensor like the Raven Biotech unit creates a closed-loop proportional integral derivative, or PID, control system. Think of it kind of like setting the cruise control in your car.
Okay, I'm with you so far.
Right. So it's like setting your cruise control to exactly 65 miles per hour. If you hit a hill, the engine automatically throttles up. If you go down a slope, it pulls back. In the bioreactor, the PID loop ensures the methanol concentration never drops too low to stall the AOX1 promoter, and it never goes so fast that you crash into toxic substrate inhibition. Prior to this kind of immediate hardware integration, operators relied on assumptions or offline sampling that took hours.
Which left massive windows where methanol could accumulate.
Exactly. By locking in a target of exactly 1.0 to 2.0 grams per liter, we establish an immovable environmental guardrail.
It is a beautifully clean engineering concept, but I come at it from a different way. A bioreactor isn't a car on a flat, predictable highway. It's a highly complex, constantly shifting biological ecosystem. To use your analogy, the PID loop measuring the tank concentration is just measuring the speed of the treadmill. But the RQ analysis, the off-gas analysis, is like strapping a VO2 max mask onto an athlete.
Measuring their actual oxygen intake.
Exactly. The treadmill speed might say 6 miles per hour, which sounds perfectly safe. But the oxygen mask tells us if the athlete is actually suffocating under the workload. The respiratory quotient is the ratio of carbon dioxide produced to oxygen consumed. It tells us exactly how the cell is utilizing the methanol. If you simply maintain a 1.5 gram per liter concentration, you might be overwhelming a stressed, low-density culture. Or, conversely, you might be starving a highly dense, hyperactive culture.
But doesn't that metabolic monitoring leave you constantly playing catch-up? By the time you detect a shift in the off-gas, the metabolic stress has already begun. The sensor prevents this stress from happening in the first place by never letting the concentration fluctuate.
I'm sorry, but I just don't buy that. Let me tell you why. Cellular respiration happens on a continuous, real-time basis. The carbon dioxide exhaled into the off-gas is a direct, immediate byproduct of the metabolic pathways we are actively trying to optimize. It is not a trailing indicator. It's a real-time window into the cell's enzymatic processing.
Even so,
if the RQ deviates from that optimal 0.65 to 0.75 range, it means the metabolism is bottlenecking, regardless of what the tank concentration says. A concentration of 1.5 grams per liter might be perfectly safe at hour 20, but highly toxic at hour 40 depending on the accumulated stress of the biomass. The RQ target adapts to the cell's reality, not an arbitrary set point engineered on a chalkboard.
that's an interesting point, though I would frame it differently. The set point of 1.0 to 2.0 grams per liter is not arbitrary. It is the established kinetic sweet spot for Pichia pastoris. Decades of bioprocessing data show this is the exact threshold required to saturate the transport proteins and sustain the AOX1 promoter without triggering inhibition. But let's look at the actual outcomes from the source material, because this is where the theoretical meets the practical. This kit delivers two massive quick wins, a 40% reduction in induction phase duration and a 25% increase in titer.
Which are incredible numbers for any facility.
Staggering numbers! A 40% reduction in time completely alters the economics of a biomanufacturing plant. It means you can turn over batches almost twice as fast, minimizing facility downtime and labor costs. And I firmly posit that this 40% reduction in time is directly attributable to the closed-loop PID control.
How so?
Because time is purely a function of constant, uninterrupted catalytic activity. When you use the Raven Biotech sensor to aggressively defend that optimal lower bound of 1.0 gram per liter, the cells are never starved. There are no microscopic periods of famine where the induction machinery shuts down. The feed is relentless and optimized. A constant, precisely controlled external feed naturally equates to a faster, shorter induction phase.
While a faster process is highly desirable, and it certainly saves money on facility overhead, I have to challenge the prioritization of time over yield. When we evaluate bioprocessing optimization, that 25% titer increase is arguably the far more crucial metric.
You really think the yield is more important than a 40% cut in time?
Absolutely. In biopharma, downstream processing and purification costs are relatively fixed. If you can get 25% more target protein out of the same volume of liquid, that is pure margin. You can finish a run 40% faster, but if your yield is compromised because the cells are stressed, you haven't truly optimized the economic or biological output of the reactor. The source material explicitly links the titer increase to reduce cell stress.
Right, which the PID loop achieves by maintaining stability.
But stability of the environment does not guarantee stability of the cell. If you rely purely on the PID loop and just mechanically dump methanol into the reactor to blindly hit that 1.5 gram per liter target, you run a severe risk of inducing unseen cellular stress. The off-gas analysis, by actively maintaining that strict RQ of 0.65 to 0.75, ensures that the metabolic burden of processing the methanol is perfectly balanced with the massive energy required for recombinant protein synthesis. The RQ control strategy is the direct architect of that 25% yield boost. It is the mechanism that actually reduces the cell stress.
I see why you think that, but let me give you a different perspective on how those two metrics, time and yield, interact. I don't believe you can separate the yield from the time saved.
Go on.
A 40% reduction in induction phase duration inherently reduces the cumulative stress a culture experiences. Think about what a cell goes through inside a 10,000-liter bioreactor. It's a violent environment. You have massive impeller blades causing physical shear stress. You have localized zones of oxygen depletion, osmotic pressure, changing viscosities.
It's essentially a washing machine for microbes.
Exactly. It's a highly hostile environment. By utilizing the sensor to aggressively maintain the methanol concentration, we push the cells through the induction phase at maximum metabolic velocity. The 25% tighter increase is a secondary benefit of finishing the process quickly and cleanly, before late-stage toxicity, shear stress accumulation, and cell death can occur. The hardware-driven PID control is the engine driving the speed, and the speed is what protects the yield.
That's a compelling argument. But have you considered the biochemical mechanism of the AOX1 promoter itself? Because it is highly sensitive to the quality of the metabolism, not just the raw availability of the inducer.
We're talking about the breakdown of methanol into formaldehyde.
Yes. When Pichia metabolizes methanol, the very first step in the pathway produces formaldehyde and hydrogen peroxide. Both are incredibly toxic to the cell. Now, if the metabolic flux is too high, even if your fancy Raven Biotech sensor perfectly holds the tank concentration at exactly 1.5 grams per liter, formaldehyde can begin to accumulate intracellularly. The cell takes the methanol in, but it can't process the toxic intermediates fast enough.
And your point is that the sensor can't see inside the cell.
The PID loop is completely blind to intracellular formaldehyde accumulation. It just sees the methanol in the tank and keeps feeding. The respiratory quotient, however, shifts the absolute moment this metabolic bottleneck occurs. By targeting an RQ of 0.65 to 0.75, we are essentially monitoring the cell's ability to safely clear those toxic intermediates. We are listening to the cell say, I am processing the formaldehyde safely. This physiological monitoring is what keeps the cell viable, allowing it to act as a factory for our target protein at a 25% higher titer. The reduction in time is beneficial, yes, but the physiological mastery provided by off-gas analysis is what actually secures the biological viability to achieve that titer.
I'm not convinced by that line of reasoning because it somewhat underestimates the adaptability of the closed-loop system. And perhaps more importantly, it ignores the operational reality of the solution kit described in the text.
You're talking about the 10 to 14-day implementation window.
Yes. Let's talk about what that actually means for a facility. Normally, overhauling a feeding strategy requires months of pilot runs, incredibly complex metabolic modeling, and immense historical data to establish baselines. This entire optimization is designed to be deployed in a mere 10 to 14 days. From an operational and engineering standpoint, the practicality of the direct control method cannot be overstated.
It is undeniably fast to install a sensor.
It's entirely plug-and-play. You drop the online methanol sensor directly into the reactor. You establish an immediate hardware-based closed loop. You set the PID parameters, you input the 1.0 to 2.0 grams per liter target, and the system actively and immediately prevents toxicity through strict mechanical regulation. For a facility looking for a rapid turnaround, perhaps they are experiencing batch failures and need an immediate fix, the sensor and PID loop offer a robust, definitive barrier against catastrophic process failure without needing a team of data scientists to interpret respiratory models.
I absolutely acknowledge the immense utility and operational elegance of that hardware. Dropping a modern sensor into a bioreactor gives you an immediate feedback loop that is undeniably powerful. But I maintain that off-gas analysis represents a far more sophisticated conceptual framework, which is why it must be the governing principle of the solution kit even in a rapid deployment.
Even though the sensor does the heavy lifting of physical control?
Because a PID loop, for all of its mathematical precision and rapid response time, is entirely subordinate to the set point it is given. It is a blind servant to a number. If the biological reality dictates that a particular culture simply cannot handle 1.0 gram per liter on day 3 without experiencing that severe intracellular stress we talked about, the PID loop doesn't care. It will still mechanically force the feed to reach that target, potentially ruining the batch.
But again, that's why the 1.0 to 2.0 range is a tested kinetic sweet spot.
But the environment is never truly static. The biomass is constantly growing and changing throughout the induction phase. A concentration of 1.5 grams per liter means something entirely different to a culture at an optical density of 100 versus an optical density of 400. This is the fundamental flaw in relying solely on a fixed environmental target. Toxicity isn't just an absolute number. It is a ratio of substrate to cellular capacity.
And you're arguing the off-gas scales with that capacity naturally?
Exactly. The off-gas analysis naturally scales with the biomass. As the cell density increases, the absolute volumes of carbon dioxide exhaled and oxygen consumed will go up. But the respiratory quotient, that ratio of 0.65 to 0.75, remains a true, normalized metric of metabolic health. Implementing an RQ target within that 10 to 14-day window means you aren't just installing a mechanical loop. You are installing a system that listens to the organism. It elevates the entire process from mere chemical engineering to true biological engineering. The off-gas analysis acts as the ultimate biological authority over the mechanical loop.
That's an interesting point, though I would frame it differently. While you paint the PID loop as this rigid, unthinking mechanism, the reality is that maintaining a tight range of 1.0 to 2.0 grams per liter provides the exact stability a complex biological system requires to actually find its own metabolic equilibrium.
You think the stability creates the biological calm?
I know it does. When the external environment fluctuates wildly, which is what happens when you try to chase dynamic metabolic indicators without a hard baseline, the cell wastes immense amounts of ATP, constantly upregulating and downregulating various transport proteins, stress response genes, and metabolic pathways.
The cell exhausts itself trying to adapt.
Precisely. By using the online methanol sensor to create a rock-solid, unchanging external environment, we remove a massive source of exogenous stress. The cells no longer have to adapt to oscillating methanol concentrations. They can devote all their cellular machinery, all that ATP, purely to AOX1 induction and protein synthesis. Therefore, the physical control of the environment is the prerequisite for the biological calm you are measuring with your off-gas analysis. The RQ looks great because the PID loop is doing its job.
I see the logic there, but it assumes the cell's internal machinery operates at a perfectly constant rate as long as the outside is constant. And as we've discussed with formaldehyde accumulation, that just isn't the case. The physiological monitoring doesn't just measure a biological calm after the fact, it actively guides the feed rate to ensure those internal pathways remain unsaturated.
That brings us to a critical juncture in our discussion, and perhaps to the text itself. If we look closely at the source material, it clearly frames these two strategies not merely as opposing options, but as a combined solution kit intended to deliver a comprehensive process overhaul.
They are sold as a package deal for a reason.
Exactly. So, to summarize my position in light of our exchange, I maintain that precise, mechanical control of the bioreactor environment is the bedrock of this optimization. Deploying an online methanol sensor like the Raven Biotech system and utilizing closed-loop PID control to rigorously defend the concentration of 1 to 2 grams per liter physically prevents the gross accumulation of toxic substrate. I view this direct, instantaneous hardware intervention as the primary driver behind the massive 40% reduction in induction phase duration. It allows for a relentless, optimal feed rate that maximizes AOX1 induction without interruption and provides the baseline stability the cells need.
And to summarize my stance, I contend that biological processes ultimately demand physiological monitoring to achieve true optimization. While controlling the external environment with a sensor is incredibly helpful, the off-gas analysis is the indispensable key to the process. By targeting a respiratory quotient of 0.65 to 0.75, we are measuring the actual metabolic reality of the Pichia pastoris cells. This ensures that methanol is being processed efficiently without the intracellular accumulation of toxic intermediates. Therefore, it is this dynamic metabolic control strategy that is primarily responsible for the 25% titer increase, as it actively and continuously fulfills the goal of reducing cell stress.
Despite our different perspectives on which mechanism is the primary driver, there is a clear point of convergence here. We both agree that this 10 to 14-day solution kit provides an incredibly powerful, two-pronged approach. The data truly speaks for itself. A 40% reduction in time and a 25% increase in titer are undeniably massive improvements that would revolutionize any biomanufacturing facility's throughput.
Absolutely. The synergy of the two approaches is what makes the kit so effective. It perfectly illustrates how the immense complexity of bioprocessing requires us to look at the system from both a mechanical control perspective and a physiological response perspective. You cannot fully master the organism without understanding both the physical environment you put it in and how it metabolically breathes and reacts to that environment.
It certainly leaves us with a deeper appreciation for the intricacies of Pichia pastoris optimization and the engineering required to scale these microscopic processes. There is always more to explore in the material, and we leave it to you, the listener, to evaluate the evidence and determine which control strategies should be prioritized in your own bioprocessing facilities. Thank you for joining us on this intellectual journey.
You've been listening to Biomanufacturing and Fermentation Technology with Prasad Urnala. Thank you for joining me. Until next time, keep engineering biology into reliable manufacturing.